All right, I think we're okay. Okay, so just real quick, I've had a couple of visits from different students over the last 48 hours with questions over the homework for 8.1, which leads me to believe, by my familiarity with these students, they're pretty good students in the class. They're having some issues with 8.1, which leads me to believe that 8.1 is going to be a challenge. Chapter 8 is going to be a challenge for most of you, all right? And that's expected. But please reach out for help, okay? If up to this point you've been able to do fine and not need much assistance, that's great. But maybe now you are going to. So please do come into my office for help if you get a chance. My office hours are on the syllabus. I was doing those scheduled appointments for a while, and I've kind of just pulled that because it wasn't quite working out the way I wanted it to. I'd rather have 5 people there and helping everyone, you helping each other, than to have just one person there for 30 minutes. To me, I like that better. So please come by for help if you need it. There is a correction. I made a mistake on your notes last time that I want to clarify. I had, when we were talking about monotonic sequences and then bounded sequences, we had defined the idea of being bounded above is that there's basically a line that your sequence never goes above. That's what it meant to be bounded above. And bounded below is like a line below your sequence never goes below it. And what I said in class is that we call the sequence bounded if it's either bounded above or bounded below. Either or, right? One or the other. But in fact, the definition of bounded is that you must be bounded from above and bounded from below to be called bounded. All right? So if you're just bounded above and not bounded below, it's not a bounded sequence. So please correct this. So scratch, if you had this in your notes, scratch that and replace it with, if A sub n is both bounded above and below, then it is said to be bounded. And the reason why I started thinking about this after class was because after I gave you that, we had the monotonic, the theorem. Here we go. Every bounded monotonic sequence must converge. That was the big result of it. Well, you can have a monotonic sequence, let's say like this. That's a monotonic sequence. It's increasing, right? It's bounded below but not above. So does this one converge? Does it look like it converges to something? Well, I could keep making this go up forever, right? That does not converge. So if I would have stuck with my idea of what bounded meant last time, this would be bounded, it would be monotonic, but it wouldn't converge. And the theorem says that every bounded monotonic sequence must converge. So by now redefining what bounded means, that means I have to be able to smash the sequence between 2 lines. And now if it's monotonic, it's got to converge. Because if it's going up, it's got to eventually, or it's got to always stay below this line. So it's got to go to something. And if it's monotonic decreasing, then it's going to come down and do the same thing. So just a correction to start class. I do want to start 8.2 today and reserve any questions over 8.1 for the end, although I don't think we'll have time at the end. So again, I'm encouraging you to please come in and get help. And did anyone have questions on 8.1? I'm just curious if I would have said, hey, let's answer questions on 8.1. Yes? You would have had a few? Okay. Let's just see if we can maybe reserve the last few minutes for that. Remind me at the end. I'm going to get so into this here today. I enjoy almost every single thing I'm talking about today, so I might forget that you have a question on 8.1. All right, so we are going to begin series. And the rest of the chapter is pretty much about series. So a series or if you want to call it an infinite series is simply the sum of the terms of a sequence. So we are defining, okay, this is a definition of what a series is, or an infinite series. Now there are such things as finite series, where you add up, where you're adding up terms of a sequence and you stop at some point. That would be a finite series. But in general, a series usually means infinite, an infinite summation. So sequence, last two classes we spent time on what a sequence is. A sequence is just a list of numbers, right? Now what we want to do is take that list and add them up. Add each number to the next, to the next, to the next, forever. So it looks something like this. So in other words, i.e., in other words, if we're given a sequence A sub n, which is A1, A2, A3, right? And it goes forever. So if we're given a sequence, right, then the series is what? A1 plus A2 plus A3 plus forever. That's what it is. Just add them up. Now, we have a different notation we can use for this. We can use what's called sigma notation, which means that this would be equal to summation y'all have seen this symbol? We've talked about this a little bit in this class already. This means we're going to add stuff up, right? We're going to add stuff up. And we will need to start somewhere and end somewhere. Okay, so I want to start my index at k equals 1. And I want to end my index where? Well, I don't want to end it, right? I don't want to ever stop adding. So I'm going to put an infinity up here. So this is our starting index. This is our ending index. Since we don't want to end, we put infinity up here. Now, what is it that I want to add up? Well, the terms of the sequence a sub n. So I'm going to put down here, or in here next to this, a sub k. So the way this works is the sigma notation tells us we're going to start adding. We're going to first start with k being 1. I go into this expression, I replace k with 1, write that down. Then plus, now let k be 2, put k in here, add that. So if you do that, you start getting the same thing you had above, right? A1 plus A2 plus A3, and forever and ever. Make sense? This is just notation. What we're going to focus the next several weeks on is trying to figure out what happens when you start adding things up forever. And it's going to be a little bit tedious, as we're going to find out. All right, next definition. Definition of what's called a partial sum. If the infinite series is an infinite sum, right? Just keep adding forever. A partial sum should represent part of a sum, right? Not the whole thing, but part of it. So when we say partial sum, then we say this. If, again, a sub n is given to us to be some sequence of numbers. I just said sequence of numbers, didn't I? We're going to see that your sequence doesn't have to be numbers. That's what we're starting with, but later on you'll have a sequence of functions. And then when we add them up, we get that power series thing we were talking about when I first introduced what we're doing in this chapter. Remember I showed you what e to the x really was? And it went forever. Okay, so right now this is a sequence of numbers. But if we're given this infinite sequence, and I want to talk about a partial sum, then I can call, maybe I can define S for sum S1 as being just the sum of the first term. So that would be just A1. And then maybe I define S2 to be what? The sum of the first two, right? So like A1 plus A2. And then S3 would be the sum of the first three terms. And I could keep going, right? S sub n would be A1 plus A2 all the way till I get out to where? AN, and I stop, right? It's a partial sum, so I stop. This one right here is what we call the nth partial sum. You'll hear me say that in this class. So when I say we look at the nth partial sum, I'm talking about the sum of the first n parts, sum of the first n terms of the sequence. Now, I can also write S sub n a different way because this is kind of tedious. I could do it in sigma notation instead. I could write S sub n is actually summation k equals 1. This time I do want to stop it, right? Where do I want to stop it? At n. So I go to n, and what am I adding up? A sub k, right? A sub k. So this would be a sub 1 plus a sub 2 plus a sub 3 all the way till I get to a sub n. So that is, these are equivalent expressions. Those both represent the nth partial sum. Now, anybody notice anything here? S1, S2, S3, S dot, dot, dot. Anybody recognize what we actually just created? Okay, well, let me write this. What is A sub n? A sub n is just a sequence of numbers, right? Didn't we just create a new sequence of numbers? S1 is a number, isn't it? S2 is a number. It's just add two things together. S3 is a number. S4 is a number, right? So we need to notice here, that the sequence, S sub n. Now, I'm putting braces around the S sub n because I want you to understand the difference between me writing this and me writing this. S sub n is the nth partial sum, right? But if you look at S sub n here, what I really mean is n equals 1 to infinity, right? I usually didn't write that. I'll go back. Let me go back in my notes real quick so you can see what I'm talking about. This would have been the first day that we introduced this stuff. Notation. Here we go. There we go. Okay? I had said that if you put a brace around here, this tells you where you start and where you stop, or you could just write it, you know, A sub n. What I'm doing right now is when I'm writing S sub n, I really mean this, right? But don't confuse that with the nth partial sum, which is this. This list of numbers, S1, S2, S3, S4, S5, all those is a sequence of numbers. Do y'all agree with that? Okay, so let me again try and make sure that we're all on the same page. A sub n is a sequence of numbers, right? A sub n is a sequence of numbers. What I can do is start adding those sequences up, or the sequence up. If I look at just the first term, that's it right there, right? That's A sub 1 by itself. S sub 2 is A sub 1 plus A sub 2. S sub 3 is A sub 1 plus A sub 2 plus A sub 3. S sub 4 is A1, A2, A3, A4, right? When I add those, right, I get numbers here. This now represents a new sequence of numbers, new sequence. So this is a sequence of numbers generated by adding up the terms of the sequence of a different sequence. Does that make sense or not? We're going to do an example of this, but if we have a new sequence that is created from that a sub n, then what do you think we're interested about this in with this sequence? What it does, right? Does it converge? That's a great question. If a sub n converges, then does that converge? Let's think about that for a second. What if I had a sequence a sub n that was just 1, 1, 1, 1, 1, 1, 1, 1? Okay? Now start adding them up. Your first one would be 1. Your second one would be 1 plus 1, which would be 2. Next one would be 1 plus 1 plus 1, which would be 3. You following? Then 4, then 5, then 6. Is that converging? No, that's diverging. You see what I'm saying? So just because the sequence converges does not mean that the sum, the series converges. So our question is actually for the rest of today and the next class is going to be, what conditions must be met in order to say that this converges or diverges? All right? Hope you're following along. Let's take a look at an example. I'm going to put something here. This is a sub 1. This is a sub 1 plus a sub 2. A sub 1 plus a sub 2 plus a sub 3, just to remind you where those came from. I already had that written up here, didn't I? I mean, it's right here, but I'm just putting it here again to remind you. All right. Let's take a look at an example before we actually get too much further into this. I'm going to define a sequence for you. Let a sub n equal 1 over 2 to the n. That's a perfect example of something that you would have been given in your 8.1 homework, and you would have been asked, does this sequence converge? Right? Does this sequence converge? What I'd like for us to just take a look at right now is not the sequence itself, but the series. Let's look at the nth partial sums instead. So what I will do first, let's write out some terms of this sequence. So the sequence right here is equal to, I'm starting n where? At 1. So if I plug in 1, what do I get? 1/2. I plug in 2, I get 1/4, and then 1/8, 1/16. I'll do one more. 1/32. This reminds me of something real quick off the subject, but I'm still kind of related to what we're doing. Have y'all ever noticed that when you buy like computers and memory sticks and different things, that they always do things in these using these numbers like 8, 16, 32, 64, 128. Have you ever noticed that? There's always powers of 2. Have you ever wondered why? Because it's binary, right? Y'all know that? Good. Because computers are all binary, zeros or ones, all base 2. So everything's basically powers of 2. That's why. All right. Good. You already knew that. Just want to make sure. All right, so now that's just our sequence, nothing new here. Now let's look at the series, and we're going to look at the nth partial sums. So what would S1 be here for us? Just 1/2. What would S2 be? 1/2 plus 1/4, which would be 3/4. We'd have to get a common denominator, right? And then we have S3, which would be 1/2 plus 1/4 plus 1/8, right? Which is, I wonder if I did this, 7/8. And then S4, which is, I'm not going to write everything out, it's 15/16. And you can kind of see a pattern here, can't you? Isn't the denominator is always one more than the numerator? So the next one will probably be what? 31, 30 seconds, something like that. But you can see that this right here is a new sequence of numbers, right? And let me write those down as a sequence. It's 1/2, 3/4, 7/8, 15/16, ... This right here is my sequence S sub n, right? That's my sequence S sub n. And now the question becomes, what do you think is happening to this sequence? Do you think that that's converging or diverging? Looks like it might be converging, right? To what? To 1? Looks like it. So I have some Mathematica stuff I did here. Let me put that sequence in. It was 1 over 2 to the n, right? All right, so what you see here now are two different graphs. Before I always just showed you the graph of the sequence. So make sure you see what's going on here. I'll make these points a little bigger so you can see them. Okay, so the left one is A sub n. If we plugged in 1, we got what? 1/2. We plug in 2, we get 1/4. We plug in 3, we get 1/8, 1/16, 1/32, 1/64, right? So this is our sequence A sub n. Then over here is the actual sequence S sub n. So we said S sub 1 was what? 1/2. We said S sub 2 was 1/2 plus 1/4, which is this, right? Then we said S sub 3 would be 1/2 plus 1/4 plus 1/8, right? And then this next one is, right? And look at this sequence over here. If I start adding more points, look what happens. Right? We know this converges to 0. 1 over 2 to the n went to 0. The original sequence went to 0. The series appears to be approaching 1, doesn't it? So maybe it's that if this converges to 0, that has to converge. I don't know. Again, we can start making conjectures, but we're going to have to convince ourselves. What do you think? What does your instinct tell you? If this goes to 0, do you think that means this has to converge? No? Let me give you another one. Another 1 over n squared. 1 over n squared. Let's see. So 1 over n squared starts out at 1, and then you go, what, you plug in 2. 2 squared is 4, so this is 1/4. And then you plug in 3. 3 squared is 9, so 1/9. Got it? 1/16. And then you keep going. That's converging to 0. And then look at the series. Does it look like the series is converging? Not to 1, but does it look like it's converging to something? Does? I only programmed it to go out to 250, but you might argue that, yeah, that maybe, I don't know. I mean, that might be growing, right? Very slowly. I might have to go out 1,000,000 terms to make it go up to 1.7, but I mean, the thing is, I'm going to infinity. I don't have to stop ever, right? So maybe it is, maybe it isn't. Let's look at another one. Instead of 1 over n squared, how about just 1 over n? 1 over n, that goes to 0, right? The sequence 1 over n goes to 0 as n goes to infinity. Let's see what the series does. So here's the sequences going to 0, right? Look at the series. Now this one looks like it's growing pretty quick, doesn't it? And what's going to happen is I start pulling this thing out. It's still growing, right? Looks like it's slowing down, but it is still growing, right? So the question becomes, does that converge or diverge? And do you see the dilemma here? I mean, we want to try and convince ourselves when things do and do not converge. Okay. I just wanted you to see kind of visually what's happening. So this note right here, I'm not doing any more investigation. This was just to practice writing out a sequence and writing out the partial sums. What we don't have, and I will point this out right now, what we don't have is a formula for S sub n right now, right? Like, if I look back up here, A sub n was well defined, right? Explicitly, 1 over 2 to the n. If I wanted to know the 1,000th term of this sequence, right, I would just plug 1,000 in and I'd be done. Here, to get the 1,000th, I would actually need to add up the first 1,000, right? Now, I think we saw that there was a pattern, but you know, that's just because there was a pattern in this one, right? In general, I don't actually have a formula. The only thing I actually know is that if I want S sub n, the nth sum, it's going to be, what, 1/2 plus 1/4, right? Plus 1/8 all the way out to what? 1 over 2 to the n, correct? That's the exact formula for S sub n, the nth sum. But how do I deal with all that crap in here, right? Another way I could have written it is this way. Sigma notation, k equals 1 to n of 1 over 2 to the k. So that is a formula, right? This formula right here gives me this summation, right? Starts at 1, ends at n. But you can't just look at this right here. Well, not yet. You can't look at this and just tell me what's going to happen. We are going to be able to do that. But do you agree right now that if I asked you for the 1,000th, you know, S sub 1,000, you can't just grind the answer out real quick, right? You can't just pop it out like you could here, although 2 to the 1,000 would probably give you like an overflow error on your calculator. But theoretically, we know that the 1,000th term of this sequence is 1 over 2 to the 1,000th power. Done. Here, what is it? Well, we got to add all that up. Okay, let's now talk a little bit about some major results. All right, so this is kind of like a theorem. If A sub n converges to L, and L is not 0, then what do you think the conclusion is? What diverges? The series will diverge. So let me give you an example of something that does this, all right? As an example, let's say we have A sub n equals n over n plus 1. In your homework for 8.1, you'd be asked, does this sequence converge or diverge? And you would go and you'd let n go to infinity, and perhaps you would divide everything by n, or maybe you would do L'Hopital's rule, switch it to a function of x, bring it back, whatever. But what you would figure out is that A sub n here converges to 1, all right? As you plug in higher and bigger values of n, this thing goes to 1, all right? That's what you would have done from 8.1. So what we have is a sequence whose limit is L, but L here is not 0. So if each of the terms of the sequence are getting closer and closer to 1, and then I'm adding them up, right? That's what S sub n means. I'm adding up numbers that keep getting a little bit bigger, and they keep getting closer to 1. So it's basically like adding up 1 plus 1 plus 1 plus 1 forever, which is just going to blow up, right? It's going to become infinite. Does that make sense? So that's why this series will diverge, because this series is not going anywhere. It's going to infinity, not going to a specific number. So this is a real quick check, okay? If you want to see if a series diverges, if you want to check, the first thing you can do is take the limit of the sequence. If the sequence A sub n, if it goes somewhere other than 0, you are done. It's over. The series diverges. Students will forget that this is available to them, and they'll start trying to hack away at these series, and then I'll be like, hey, what does the little sequence go to? Oh, it goes to 2. Okay, then you're done, right? You don't have to talk about the series anymore. So this is always our first check. Remember, the big picture is that we're gonna be given series, and we're gonna be asked if they converge or diverge. And we have all these different attacks we're gonna have for the different series. The first attack is to check this. All right? Let me give you one more example of this. Find the sum k equals 1 to infinity. Okay. Natural logs, first thing came to my mind. No. Yeah. Oh, yeah. Kind of, I'm committed now. Damn it. Okay. Oh, that changed that n to a k. Sorry. K right in there. So what we need to recognize here is that this right here is actually our a sub n, but written with an index a sub k. I'm just replacing the n with k. The reason why I'm not using n is, well, I guess I could have used n, huh? Because I'm not stopping, I'm going to infinity. So, but in the way I first introduced the summation, I used k here, right? So I'm going to keep it k. So this is our a sub k. The thing inside the series, right? Inside the summation, that's our a sub k. So you could start trying to add this crap up, right? Plug in 1, then plug in 2, then plug in 3, and add, keep adding. But before you do that, you want to check this. Is the sequence itself, is this approaching a number other than 0? So let's look at this right here. Let's take the limit as k goes to infinity of natural log of 2 plus 1 over k. And what is it? Well, 1 over k, as k goes to infinity, goes to what? 0. 2 plus 0 is 2. This just goes to the natural log of 2, doesn't it? The natural log of 2 is a number. Is it 0? No, that's not 0. So I know that this sequence, right, is converging to something other than 0, which means that this summation diverges. And I'm done. So all I say is, since a sub k approaches natural log 2, which is not 0, we have, that implies that the summation k equals 1 to n of natural log 2 plus 1 over k diverges. Now I wrote quite a bit of detail here. I hope that you realize that that's detail. I'm summarizing everything. I'm explaining why it's diverging, right? Since this goes to 0, since the thing inside goes to 0, I can now conclude that this diverges. And this is one of the things you're going to have to get used to. I remember I said there's going to be like a list of things that we're going to use to attack these problems. I said the challenge is, a lot of times you'll know which one to use, but it's using it properly and drawing your conclusion properly. I can conclude this diverges, and I've laid it out, and you will have to lay out to me clearly in words and in sentences, perhaps, explaining the logic behind your conclusion. If you are doing a test and you look at something, you're just like, it looks like it converges, and you write it converges, you don't have any justification for it, I can't give you any credit for it. You have to support your conclusion with rationale, all right? Can't be a coin flip. Now let me go back in here. I'm going to actually type in that series, the sequence. It was log 2 plus 1 over n, right? So you can see that the sequence itself converged to log 2, right? Whatever log 2 is. And since it converges to something other than 0, 0's down here, automatically the series diverges. Look at it, it's taken off to infinity. It looks almost linear, doesn't it? Doesn't this almost look linear? It's because you're basically adding natural log 2 plus natural log 2 plus natural log 2. So it's like almost like the slope of that line is like natural log 2. It's constant change. Okay, questions? Yes. You could have just written this. If you would have instead of this, you could have just said since that goes 0, you could have just written S sub n diverges. As long as we both understand that you mean the series diverges, the series that is represented by the sums of that sequence. That's fine with me. All right. So let me just do a quick little summary of things here, and then we'll start getting into today's material, the fun stuff. All right, so far, here's what we have. All right, this is only so far. I just want to make sure we got it all laid out. All right, if the limit as n goes to infinity of a sub n does not exist or is not equal to 0. All right, so we just talked about if it's not 0, right? If that limit is not 0, we said the series diverge, right? But it also turns out that if this limit doesn't exist, like the cosine one, jumping back and forth, if it doesn't exist, we will conclude that the series diverges. So in either one of those cases, so if that, then S sub n diverges. That's the first thing we have. The next thing, and this is new, okay, this is a new theorem. It's just another way of writing this, okay? But watch the way I write this. If S sub n converges, then A sub n what? Must go to 0. Now, some of you may have some background with logic, like truth tables. I don't know, maybe you've seen things like this. So I'll just look at it real quick. If we have a statement that says something like this, if P, then Q, an example underneath that would be if you're in 2414 class, my class right now, then you go to Northwest Vista College. Would you agree that this is a true statement? If you're in this class, then you are at Northwest Vista College. Yes? Okay. Does that work the other way around? It doesn't work the other way around, right? If you're at Northwest Vista College, that does not mean that you're in this class, right? You could be, but it doesn't force you to, right? So when we have if-then statements, you can't just switch the order and go the other way. Now, what if you have a statement that works both ways? It works this way and this way. Then we write P if and only if Q. And if and only if means you can go both directions and it works. But what I'm getting at is this. What if I wrote this? If not NVC, then not 2414. Is that true? That is true, right? It's called the contrapositive statement of this. So if P then Q is equivalent to if not Q, then not P. So these two statements are logically equivalent. If P then Q is the same as if not Q, then not P. So what we have here is if this limit does not exist, doesn't go to 0, right? If that doesn't happen, then that diverges. The opposite of this, or the contrapositive, would be what? If not diverge, which means if converge, then not this, which means that. Does that make any sense at all? So this is saying if you're in 2414, then you are in Northwest Vista College. This is saying if you're not in Northwest Vista College, then you're not in 2414. So the negation of this statement is that it must converge, and then the negation of this statement is that it must converge. So that's what this theorem is saying. If this series converges, I guarantee you the sequence went to 0. But we have to be careful, right? What do we have to be careful with? That statement. Careful. We are not saying that if this goes to 0, then this, what, converges? We are not saying this, okay? We are not saying that. So if you look at a sequence and you say, hey, it goes to 0, oh, it converges. That means the series converges. It's wrong. This chapter would be way too easy if that were the case. Okay, because all you'd be doing is taking limits the whole time, trying to figure out when it goes 0. If it does, you're done. If it doesn't, you're done. Unfortunately, didn't work. And I showed you that example, right? We did 1 over n squared. We kind of couldn't tell. We did 1 over n. It looked like it was taken off. Both of them went to 0, but we couldn't quite tell over here. So under what conditions will this be true? Like, under what conditions will we actually have the convergence and guarantee it? All right. Some more definitions. We're almost ready to get into some cool stuff. Given a sub n. Okay, so if you're given a sub n, we already know that S sub n is a new sequence created from that, right? A new sequence. If S sub n converges to something C, I'm going to use C instead of L so we don't confuse it with the sequence up there, A sub n. If S sub n converges to L, then we say the series is convergent. C is the sum of the series. And lastly, if S sub n diverges, we say, this is just language, okay? We say the series is divergent. So just language, all right? That's all it is, just some language. Three important series. when it comes to series, these three series that I'm about to talk about come up a lot. They're very important that you understand them. It's going to make your life a lot easier. So we're going to attack these one at a time. All right? I'm going to try and get through all three today. Let's see. The first one, I'll list them out first, then we'll go attack them. All right, the first one is what's called a geometric series. The second one is called a harmonic series. And the third one is called a telescopic or a collapsing series. So what happens is we get to a point in a couple of days, in a couple of weeks, where we're looking at some series, and we just look at it. It takes us about 3 or 4 seconds. We go, oh, that's geometric. And we recognize it right away because all of these have different characteristics to them. If it's geometric, it has certain pattern, and certain things happen to geometric series. Harmonic, same thing. We'll be able to look at, hey, wait, that's harmonic. Since it's harmonic, it does this. All right? So we want to be able to identify, just by looking at a series at some point, we want to be able to identify these when we see them. So we will start with geometric series. Okay, every geometric series can be written as follows. It looks like this. It's a series, so it's a sum, right? It's some number A plus A times R plus A times R squared plus A times R cubed plus A times R to the fourth plus forever and ever and ever. All geometric series look like that. Here, A is a number. Okay, I should probably state this. A and R are both real numbers. So A and R are elements. We've talked about this before. The little E symbol is element of the real numbers. So A and R are both elements of the real numbers. They're just numbers, okay? Real numbers. Now I'd like to talk about what that looks like in a sigma notation. What does a series like that look like in sigma notation? Well, I'm going to start at k equals 1. I'm going to stop never, so I'm going to stop at infinity. What stays the same in a geometric series all the time? That A, right? There's some constant in every geometric series that's always there. It might be a 1, it might be something else, but it's a constant. So here's A. Then what follows it is R being raised to various powers, right? And those powers keep coming up as you keep going down in the series. So I'm going to need to put here R to the K. Now be careful, because if I do R to the K, is that going to work? No, because when I start at 1, I get what? If I were to start here, I get AR to the 1, which would be AR, and I'm missing the A, right? So I should start, I could start it at 0 here, couldn't I? Or I could just say K minus 1 up here, which is the way I'm going to do it. If I just take away 1 from the exponent here, now if I start at K equals 1, this exponent starts at 0. That gives me the first one. Then it goes up to 2, which would give me a 1 here, and then keep going, right? Does everyone agree that that's it? Okay. Now, our question is, does this series converge? Well, what do you think it's going to depend on? It's probably going to depend on R, right? because r is the thing being raised to the power. If that r is, let's say, 2, then you're going to have like a number plus a number times 2 plus a number times 4 plus a number times 8. And that's just going to get huge, isn't it? So I don't know. How would we attack this? How would we approach this, right? R would have to be less than 1. What do y'all think about that? Didn't we talk about in class last time a sequence? You're on the right track, but we're going to run into a little bit of an issue there. No, it wasn't that one. Was it here? Maybe it was the class before. We had r to the n. It was last class? Towards the beginning or end? Beginning? Oh, there it was, right? We said that if you have r to a power in a sequence, that the thing would go to 0 if that absolute value, well, if the r was between -1 and 1, right? And that it would go to 1 if r was 1, and it would diverge any other time, yes? So when we are looking at this today, we know that the sequence, right, not the series, not adding them up, but we know this sequence here is going to go to something other than 0 if what? If that r is basically greater than 1 or less than -1, right? It's going to diverge. Do y'all agree with that? And our guess would be that if it's smaller than 1 or between -1 and 1, our guess would be that it converges, right? But that would be a guess, because just because the sequence converges does not mean the series converges, right? It might turn out that this is going to diverge all the time. So let me show you how we can approach this, all right? Just try and follow my logic here. Follow the notation, see if it makes sense. I'm going to I'm going to write out the nth partial sum of this geometric series, which means a plus ar plus ar squared plus ar cubed, all the way until I get to where? ar to the n, right? That's what the nth partial sum means. Now what I'd like to do is something that you probably never in your life would have thought to do, and I wouldn't have either until someone showed it to me, is I'd like to multiply both sides of this equation by r. So what is r times s sub n? It would become a r, right? Plus a what? R squared plus a r cubed. And you can just keep doing this, right? Plus a r to the 4th plus, and then all the way till you get down to the last one, which would be a r to the n plus 1. So by multiplying both sides of the equation by r, assuming r is not 0, right? When you multiply both sides of an equation by something, you have to promise me it's not 0. So do y'all promise it's not 0? Yes? Well, would this thing even make sense if r was 0? It would just be the sum of 0. 0 plus 0, that would converge, wouldn't it? Yeah, that would converge to 0. You would be adding up nothing. So the answer would be 0. Okay, now the very kind of tricky, unnatural thing. Other than that, I would like for us to subtract these two. In other words, take s sub n. I'd like for you to subtract from it rs sub n. Tell me what you get. So I'm going to start with this one, right? I'm going to subtract this one. Well, we'll subtract this entire row. So take this row and subtract this row and tell me what you get. What cancels here? ARs, right? AR squareds cancel. AR cubes cancel. Everything cancels. What about this last one right here? ARN. Does it cancel? Yeah, it's not infinite. Okay, it is not infinite right now. It would cancel with this one right here, right? The one right in front of AR to the n plus 1 is sitting here. I'll write it in here. Is AR to the n, isn't it? So that one would cancel with that one. But would this last one cancel with anything? No. So I would have the A from the beginning, right? And then I would have minus, right, because I'm subtracting this row. I'd have minus AR to the n plus 1. Do you agree? Now check this out. On the left side, factor out an S sub n. Factor it out. What would you be left with if you factored it out? Times 1 minus r here, right? Equals a minus a r to the n plus 1. Now, what I'm trying to do is get a formula for S sub n. I'm doing it a very tricky way, but divide both sides now by 1 minus r, and you have isolated S sub n. Check this out. This is really actually pretty cool, because what it's saying is that we had started out with S sub n being this plus this plus this all the way out to n, right? So you would have had to have added all those up. But now we're turning out by doing some really cool, tricky stuff. We're saying if you really want to know what all that adds up to be, all you really have to do is take A, which we know, right? Minus A, which we know, times R, which we know, to the n plus 1. So I just need to raise R to that power. And that's it. And then divide by 1 minus R, and that's the sum. You don't actually have to go add up a bunch. That will give you that sum. Okay? You all right with that? Not done. Next page. So factor out an A on top. You'll be left with 1 minus R to the n plus 1 all over 1 minus R. I'm going to box that for now, although that's not like a final answer, but we've kind of gotten to the cleanest point. We all agree with this? Okay, yeah, let's start talking about that. Right now, we can look at this, and we can tell that if R is 1, we've got big time problems, don't we? We have division by 0. R can't be 1. But didn't we kind of already know that if R was 1 here, then this just would have been A plus A plus A plus A plus A forever, and it would have diverged? The sum would have diverged anyway? So I don't really have to consider that because it doesn't matter. It's not going to affect this. So what happens then? What would happen if I wanted to find the infinite series? The infinite series, I want to take the partial sum, but I wouldn't want to stop, would I? I would want to let n go where? To infinity. So why don't we take the limit as n goes to infinity of this and see what happens? So the limit as n goes to infinity of S sub n is equal to the limit as n goes to infinity of A times 1 minus R to the n plus 1 over 1 minus R. And I will highlight here the only thing that's affected by the limit, right? A is a constant, R is a constant, n is the thing that's going to infinity. So I just need to figure out what's happening to this right here. What's R to the infinity? Well, it depends on R, doesn't it? So again, go back to last class. What did we say? R raised to the n would converge to 0 if what? So here's some conclusions here. If the R was between -1 and 1, what did we say that this would go to? It would go to 0, right? If that goes to 0, then what does this become? A times 1 minus 0. 1 minus 0, so A times 1, which is A, over 1 minus R. Then S sub n if that, then S sub n converges to A over 1 minus R. What would happen if R, well, if else, okay? I'll say else. Oh, hold on. Not equal to 1, sorry. Get that out of there. That's a big mistake by me. Between -1 and 1, right? If it's 1, we already said we have major problems, right? So if R is not in this interval, it's either going to go to 1 or it's going to diverge the sequence. So from notes from last class. So in either one of those cases, as long as it's not this S sub n should do what? Diverges. This is a major result right here, because it is actually, not only are we able to tell, not only are we able to tell when a geometric series converges, we're saying it converges when R is between -1 and 1, right? Not only are we saying when it converges, we are actually saying what it converges to. The sum, the infinite sum, converges to a number, and that's the number, A over 1 minus R. So let me do an example, all right, to show you a geometric series converging. Find the sum of 1 plus a half plus a fourth plus an eighth plus a 16th plus ... forever. Find the sum. What you cannot do on your test is get into your calculator and start typing this out and go, man, I think it's going to this, and put that as your answer. I mean, you have to show everything here. So first thing I'm going to do is try and come up with the sequence that creates that series. What sequence creates the series? A sub n equals 1 over two to the n. At first it looks like these are evens, but then wait a minute, we're missing 6. Then maybe you were thinking squared, but wait, 2 is not anything squared, right? But then I think you all saw it's powers of 2. 2 to the n. But hold on, if we start at n equals 1, then this is going to give us, it would start here, wouldn't it? So why don't I, what do you want to do? You can subtract 1 from that up there. Would that work? Yes, that would work. That would create each of those terms of the series, wouldn't it? Okay, so now let's rewrite that series in sigma notation using that formula within our summation. So I know that that series up there is the sum. Now I can use k because I've been using k, or I can use n at this point. It does not matter which one I use because my series stops where? at infinity. So the only time I don't want to use n down here is if I want to stop it at n, you know? You'd use k then n. But I'm going to stick to what the book does. I'm going to switch this to k, make it go from 1 to infinity. And then the formula now just has a slight change to it, right? It becomes 1 over 2 to the k minus 1, right? Just replacing that n with k. Do we all agree that that is our series that represents that sum? Yes? So you step back and you look at it. You say, what kind of series is that? Well, obviously, this is our first example of a geometric series. So it's geometric, right? But you need to see it's geometric. To see it's geometric means you have to see that it looks like this. Now, just FYI, a lot of times in books, and then I'll even do it throughout this semester, if I just write a sigma notation right here, like this, then it's assumed it goes to infinity, all right? And I usually won't write the index if it's kind of implied. Like we've been using k and n for our index. So you would assume, if I just wrote sigma, you would assume k starts at 1 and ends at infinity if I just write this, all right? So what, well, the k minus 1 is downstairs here, right? And over there it's upstairs, right? That's a problem. Unless we just realize that, well, you know, you really don't have to write it like that. You could write it like this. Isn't that the same exact thing? Because when you have a fraction raised to a power, doesn't that power get applied to both the numerator and denominator separately? Yes? So like that's really, you don't need to write this down, but that's really 1 to the k minus 1 over 2 to the k minus 1, isn't it? That's what this means? But what's 1 to any power? 1. So you see that this is this is this. Do you see the r to the k minus 1? Do you see it here? What's r here for us? 1/2. But we need an a. The a is the number sitting out here, which in this case is 1. So your goal here is to massage it to look like a geometric. If you think it's geometric, you need to massage it until it looks geometric exactly. Identify what a is, identify what r is. A here is 1. Oh, wait, I should say this is geometric with a being 1 and r being 1/2, right? And because r is 1/2, right, it's between -1 and 1, I know this converges, doesn't it? Therefore, the series converges. And because it's geometric, we have a formula for it. It converges to exactly a over 1 minus r, which for us is 1 over 1 minus 1/2, which would be 1 over 1/2, which is 2. The series converges to 2. Everybody got that? So back here, let me put that series in here. It's 1 over, it was 1 over 2 to the n minus 1, right? That's what it was, 1 over 2 to the n minus 1. So look, the sequence converged to 0, right? But that wasn't enough for us to be able to say if the series did. But you can see from the series that it converges to 2, right? I think we're all in agreement with that. No one's going to argue against that. It gets pretty close to 2 pretty quickly, doesn't it? And then as you keep going out, it's just getting closer and closer and closer. Another example. Find sum k equals 1 to infinity of 3 to the k plus 1 over 5 to the k, k minus 2. This is a series, right? I'm looking at it, I'm going, what kind of series is that? Well, I notice, a couple things we can start talking about. I noticed that the index, right, the k, the thing that's changing is in the exponent, right? Geometric series always have a base that's a number, and then the exponent is changing, because it's like the r to the k. So you always need for geometric a k or the index to be in your exponent. So I'm feeling good that this is probably geometric. And the fact this is the only one we talked about, it's probably geometric. But it does not look like sum AR to the k minus 1 yet. I need to get some k minus 1s up there, right? Somehow, some way. So now I'm just going to be clever with algebra, that's all. I'm going to rewrite 3 to the k plus 1 as 3 to the k minus 1 plus 1 plus 1. Hold on. Minus 1 plus 1. We did this once before. Do y'all remember when we did this? With integration? Do you remember when we did this with integration, when we were trying to get our, we'd have like a quadratic in the bottom, and we would try and get its derivative up top, so we would realize there's like a hidden 0 up there. We would add and subtract the number to make it work. I'm actually doing this where I'm saying I want k minus 1. So I write k minus 1, but then I can't just subtract 1, I have to add 1. And then I already had 1 up there, right? And then on the bottom, same exact thing. I have 5 to the k minus 2. I'm going to write 5 to the k minus 1 plus 1. But then what did I have up there, or down there? Minus 2. So I have not changed anything here, have I? But let's put these together, and then put those together, put these together, put those together. And so this sum becomes sum k equals 1 to infinity of 3 to the k minus 1 times 3 squared over 5 to the k minus 1 times 5 to the negative 1. What the hell just happened there? What happened? I split it up, right? I did this last class also. Do you agree that this is that over there? I mean, this 3 squared and 3 to the k minus 1, you would, since they have the same base, you would add the exponents. So you go k minus 1 plus 2. Well, that's what this is, k minus 1 plus 2. So I peeled off the part of it that I don't want. I don't want that 3 squared to mess with my 3 to the k minus 1. And for the same reason, I did this on the bottom. This is negative 1 right here, right? There's my k minus 1. So I do 5 to the k minus 1, and then I'm going to need to do 5 to the negative 1. Of course, if I put those back together, I get back the original problem, right? Now, I did that because These two are both raised to the same exact power now, right? So I could rewrite that as what? 3/5 to the k minus 1. And that would be my r. I still have to work with the rest of it, though. So I have k equals 1 to infinity. Let me write it this way. 9. Well, let's talk about what this is. I can do this all in one step, I think. What is 3 squared? 9. What's 5 to the negative 1? You bring that up as a 5. So it's 45, isn't it? We have 45 times, and then that other part became the 3/5 to the k minus 1. And that is exactly a geometric series. It's geometric with a what? Okay, it's geometric. A is 45. R is 3/5. Is 3/5 between negative 1 and 1? Yes, so this converges. It converges to what? Therefore, it converges to 45 over 1 minus 3/5. So 45 over 2/5, which is 225 over 2. And just leave it like that. Don't round it, okay? I want the exact answer here. That's just to illustrate some manipulation of exponents to make things work out nice, okay? I think I'm going to do something a little different today. I'm going to spend a little more time on geometric before I move into the next one, so I might exhaust the time today. And I do remember you do have a question also, so maybe. Okay, another example. Have you all ever seen this before that, like, if you take 1/10, we all know that that's 0.1, right? 1/10. 1/100th is 0.01, right? 1/1000th is 0.001, et cetera, et cetera. Okay, how about 1/9? 0.111 repeated forever, right? 1/9 is 0.1111111. And then how about 1 over 99? What is it? 0.01111? Yes or no? Is it? Are you saying 0.11 or 0.01.01? Which one is it? It's that one? 0.010101001 forever? Now, I'm pretty confident that everyone here is good with these two. And maybe this one. This one, maybe not so much, okay? But what I'm getting at is this. The two on the bottom are infinite decimals, right? It's a decimal that goes on forever, but there's a pattern there. 0.11111, there's a pattern. 0.010101, that's a pattern, right? But there is a fraction that is equivalent to that. There is a fraction that is equivalent to that. Now, if you stick a number in here that's a decimal that that never stops and never repeats, so there's no pattern to it, that's called an irrational number, and there is no fraction that represents that number. For example, pi. Pi, there is not a fraction for pi. E, there's not a fraction for e. But if there's a pattern and it repeats, okay, well, even if it doesn't stop, there's a fraction for it. Here's one that stops. 3/4 is 0.75, right? There's a pattern there. It stops, though, so it's not very interesting. So here's my question to you. Is he awake? Yeah. Nudge them. Hey, let's go. Come on. It's Wednesday, Thursday. You all right? Go walk around. You're fine? Were you asleep? All right. This is pretty interesting. You're the only one who doesn't look like you're interested. So, okay. So the question becomes, if we have a decimal that has a pattern that keeps going forever, can we recover the fraction from it? Let's see. So how about this? 0.257. 257. I don't know why I picked that number. But let's just say we have 0.257, 0.257, 0.257, 0.2. What is the fraction for that? Okay? So watch this. Do you agree that this is 2/10 plus 5/100 plus 7/1000 plus 2/10,000 plus 5/100,000 plus 7/1,000,000? So this is 2/10, this is 5/100, 7/1,000. Yes? And then this keeps going forever and ever and ever and ever, right? Now, this right here could be rewritten. These three, I could get a common denominator. I would have to multiply this first one by what? Just these three, common denominator. I need 1,000 here, so I multiply this by 100, so that becomes a 200 on top. I multiply this by 10 to make it 1,000, so I multiply that, that'll be a 50. And this one I don't need anything, so it'd become a 7. So if I combine these all over the same denominator, it would be what? 257 over 1,000. Plus, now what's the next three? Same thing. I would have to get a common denominator, but it would be 257 over the million, right? And we didn't write any more out here, but what do you think the next one would be? 257 over, we just need to, how many zeros did we add to get from here to here? Oh, wait, I left a zero out on this one, sorry. Oh, that's 1,000, right? So to get from here to here, we added 3 zeros, right? Because you're moving over 3 spots. So this should be, what is that, a gajillion? No, trillion. Who's it? Austin Powers had those weird, a gazillion, jillion dollars. All right, and this keeps going, right? Okay, we still have not found a fraction. We've found a couple of fractions, right? But there's still infinitely many of them. So now let's try and see a pattern. I have 257 over 1,000 is 10 to what power? 10 to the 3rd power plus 257, and this is 10 to the 6th power. And then this is 257, 10 to the 9th power. Do y'all agree? And this keeps going forever and ever. Now, 257 appears to stay the same in each term of the series. So guess what it is? It's our A, right? Okay. So I have this, 257, 1 over 10 to the 3rd plus 257, 1 over 10 to the 6th plus 257, 1 over 10 to the 9th, and then I keep that up. Now, are you ready for sigma notation? Are you? Let's see. Let's see if you're ready for sigma notation here. This is the sum, k equals 1 to infinity. Now, what never changes? 257. And then I have 1 over what? 10 to the, what do these keep going up by? This is 3, then 6, then 9. What would the next one be? 12, then 15, right? Aren't those just multiples of 3? 3, I'll use K. 3K, yes? So isn't this power just 3K? Isn't that right? K equals 1, what do we get? That, right? K equals 2, we get that. K equals 3, we get that. With me? We're almost there. I need this to look like this, right? Geometric series. I have some problems because I've got 3K, right? I don't have K. I need it to be K minus 1. So let me take care of the 3 first. Do you agree I could do this? Could I do that? What's 10 to the third to the K? You multiply 3 times K and get 3K, right? So what I've done is I've peeled the 3 off, and really 10 to the third power is really what, 1,000? So I could even go as far as saying that this is the same as K equals 1 to infinity, 257, what, 1 over 1,000 to the K? Y'all still there? But I don't need K, I need K minus 1. So I'm going to go one more step before I do that K minus 1. I think that all those parentheses are confusing. So how about I do this? Is that the same? Yes? Because of the 1 up top, it doesn't matter if I raise 1 to the K power in both. It's still the same as this. That happens all the time, so just get used to it. Now I'd like the minus 1, right? So I say, what, minus 1 plus 1 there? Which is sum K equals 1 to infinity, 257. And then I have what? 1 over 1,000 to the K minus 1. And then I'll do, yeah, the 1 over 1,000 to the 1. You could do it the other way around. So that's taking this and splitting it into the 2 pieces. And this 1 over 1,000 is going to come over here as a constant. It's going to be underneath the 257. We're there. Sum K equals 1 to infinity of 257 over 1,000, right? Times 1 over 1,000 to the K minus 1. That is a geometric series, right? A is what? 257 over 1,000. R is what? 1 over 1,000. Is R between -1 and 1? Yes. Does this series converge? Yes. What does it converge to? A over, that's A, over 1 minus R, which is 1/1,000th. That's what it converges to, right? What's 1 minus 1/1,000th? 999 thousandths. So I have 257 over 1,000 over 999 over 1,000, right? And then you flip it, and you get 257 over 999. Type that into your calculator, and you'll get 0.257, 257, 257, 257, 257. Right? and then your calculator rounds it. So you could make the conjecture at this point that if someone gave you a non-terminating but repeating decimal, like if someone said, hey, give me the fraction for 0.315 repeated, you might make the conjecture that it's what? 315729 over 6 nines, 99999, and that would be correct. All right? Or you could be thrown a problem like this, 0.02323, that repeats forever, right? But look at this, I just threw a huge issue into this problem. Do y'all see it? The 0 right before? Or if I would have put like a 4 here, so it was like 0.4232323, it will not be as easy as this. But what you would do is you would write this out, right? This would be 2 100ths, 3 1,000ths, and then you'd have to come up with a formula, and you would be able to do it the same exact way that we just did it, but it would be kind of messy. All right? What's that? I don't know. It's not as easy for things like that. You can't just, it's not as simple as this is. If there's nothing in between and the pattern starts right away, things are good. Okay, we have 10 minutes. I'm going to just show you what a harmonic series is. Geometric series are much more challenging than harmonic. Harmonic is going to be pretty straightforward. A harmonic series is any series that looks like this, A over K. Basically, you have a constant on top divided by your linear expression in K. Anytime you have a constant over a linear expression in K. What the heck do I mean by that? Well, I mean something like, as an example, the series 1 plus a half plus a third plus a fourth plus a fifth, okay? What's the series for this? What does it look like? The summation. It's 1 over n, right? I'm going to use 1 over k, but, right? That's what that is. It's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. So that's your series, right? Do you see that you have a constant on top? Yes? Do you see that your expression in the denominator is a linear expression in k, meaning that it's a linear expression in the variable k, which is your index? Yes? That's a harmonic series. So that denominator could be something like 2k, or it could be 2k plus 1, or anything like that. As long as it's a linear, we're good. It's harmonic. Now, what does a harmonic series do? All harmonic series diverge. Period. It's done. It's over. All right? All harmonic series diverge. That's good, right? If we can identify it's harmonic, we're done. So the difference between harmonic and geometric is, remember I said with geometric you're going to have like a base, and then the k is going to be up in the exponent? Here, for harmonic, you don't even have an exponent, right? Your k is just part of a linear expression. So let's just look at this one right here. This example right here. This actually is going to diverge. And maybe in the last 5 minutes I can convince you why it'll diverge. May I try? This is an argument by, it's not a solid argument. It's more of a see the pattern type thing. Okay, so let's see if you agree with this. 1 plus a half plus a third plus a fourth, right? I'm going to add those up forever and ever. And I'm going to write out quite a few of these. 1/5, 1/6, 1/7, 1/8, 1/9. I'll stop there. This keeps going. Okay, let's please take a look at these two right here. If I put those together with the common denominator, what would I get? What would it be? 7/12, wouldn't it? That would be 7/12. And then if I put not these two together, not these three together, but these four together, and get a common denominator, what you're going to get, let me see if I already worked it out. Well, I didn't work it out, but will you agree? Will you agree with me on this? 1/8 is smaller than 1/7, and 1/7 is smaller than 1/6, and 1/6 is smaller than 1/5. So if I had 1/8, 1/8, 1/8, 1/8 here, this would be bigger, wouldn't it? Right? If I had here plus 1/8 plus 1/8 plus 1/8 plus 1/8, this up top here is larger than this would be, yes? What's 1/8 plus 1/8 plus 1/8 plus 1/8? 4/8? That's 1/2. So that means that this up here is bigger than a half, isn't it? Now this right here is 7/12. Do you agree that's bigger than 6/12? 6/12 is 1/2. So, and then look at this right here. This first one was what? 1/2. And then this right here, 1. What I'm trying to get you to see is this. If I look at the first term here, it's bigger than a half, isn't it? The next one is exactly 1/2. The next two together are bigger than a half. The next four together are bigger than a half. And then the next, what do you think? 8 put together will be bigger than a half. Then the next 16 together will be bigger than a half. So that means that this infinite series is bigger than a half plus a half plus a half plus a half forever. And that half plus a half plus a half is basically stacking on. It's like having a sequence that its limit does not go to 0, therefore that has to diverge. I hope that's a good enough argument. I'm sorry, I'm out of time, so I have to cut that short. But that's the only way that I want to show you harmonic diverges. All right?
That's an example of a sequence that diverges plus a series, or a series diverges with a sequence.
Yes. Yes, sir. Exactly. This is an example where your series diverges, right? But the sequence of terms converges to 0. They get smaller and smaller. Problem is they don't get small fast enough. All right, well, I'm going to have to look at your homework because we've only talked about geometric and, oh wait, I have them right here. What the heck does that mean? What does T? Let's start out for page 443. Seven through 13 odds. Those are all pretty much geometric. You know what? Let's make that instead of 7 through 13, let's make it 7 through 23 odds. And I want to summarize just verbally. If someone gives you a series, what's the first thing you should check to see if you want to talk about whether or not it converges or not, what's the first thing you should look at? The sequence, and take its limit, right? If it goes to anything other than 0, you're done. The series diverges, right? If it does go to 0, then you want to be thinking what? Is it geometric or is it harmonic? Then next class we'll talk about the other type. But the problems I've given you are going to be one of those three cases. Either the sequence is going to not go to 0, so the series will diverge. The sequence will be harmonic, or the sequence will be geometric. All right? Enjoy. Ask me your question about your homework.